Okay, so now we've established a good understanding of the definition of a limit as well. So graphically and algebraically we solve limits, and then we looked at the definition of limit. Now we're going to look at techniques, and we're given theorems for some of the properties concerning limits. So basically, if I have a limit of a particular function f of x as x approaches c, that's equal to L. And I also consider a limit of a g of x function as x approaches c is equal to m. Then here's some properties or some theorems that we can use. This isn't the greatest copy. So basically, the limit of the sum is the sum of the limits. The limit of the sum is the sum of the limits. Okay, the limit of the product, and the same thing for subtraction. So down here, so these are just restated. The limit of the product is the product of the limits. Quotient, constant multiple rule just says we can pull a constant out front. Constant times the limit. That's that one. The limit of a quotient is the quotient of the limit, provided the denominator is a non-zero. Okay, that makes sense there. Remember, we can't have zero in denominator. And the limit of a difference is just the difference of the limit. So basically, these are just pretty intuitive for the most part. And our first theorem that we're going to work with is, if you're given M, B, and A, they're real numbers, and it's defined by this, then we evaluate that limit, pretty much direct substitution. So let me go to a new page. So on this one, we're just going to plug in 4. That's x approaches 6. So 24 minus 11, and what do we get here? It's 13. Okay. Our next theorem, these are just going to break them down into individual theorems. So if we have this particular case, we'll just have a to the n. If we have a function raised to the nth power, then we can do the whole entire limit raised to the nth power, provided the limit exists. Okay, so we're going to look at these two particular cases. We'll work an example. So let's go to the other page and work this particular example. Okay, our theorem allows us to rewrite this. It's the limit of our function as x approaches 2, and then raise that entire thing to the 5th power. Okay, so within here we can go, what can we do here? Direct substitution to evaluate that. So let's just say we'll have 3, plug in, evaluate our f of x there, and then we can raise it to the 5th power. So this would give us 3 times 2 is 6, plus 4 is 10. What, 10 to the 5th power? 10 to the 5th power, which is, okay, so that was theorem 2.10. We'll come back over here. Let's consider theorem 2.11. We have a polynomial function. X is a real number. This is actually the direct substitution term here. So it says evaluate your function at A. This is specifically the definition for direct substitution. So this is pretty easy. Everywhere that there's an X, we're going to substitute in a -2. But let's apply our theorem. Let's practice one of these and separate it out. We're going to use the theorem where let's see, we'll come back up here. The limit of the sum is the sum of the limits, and let me show you how that works as well. Alright, so we'll have, let me rewrite this. So we have the limit of our polynomial function, which was 5x cubed plus 3x squared minus 6. X approaches -2. Alright, so we're going to break these into individual limits. So the first term is just going to be 5x cubed. Then we can add that to the limit of our second term, which is 3x squared, as x approaches -2. And then subtract the last term, the limit of 6, as x approaches -2. the limit of the sum is the sum of the limits. Also, we can pull constants out. So let's just, for this particular case, I'm just going to practice a lot of those theorems. Now, granted, I'm not suggesting that you have to do it this way. I want you to see one. There may be a particular case on your homework where it says use the theorems to simplify this, or a specific way that you're going to break this down entirely. Okay, so we have the constant where we can pull 5 limit of x cubed as x approaches -2. So what would the next one be? 3 times the limit of what? X squared as x approaches -2 minus, and this one's just going to remain. Alright, now we're ready to evaluate this. Let me do it in a different color. So that's just going to give me 5 times -2 to the third power. Over here it's just going to be 3 times -2 squared and then minus 6. -2 cubes 8, 8 times 5. So we get 40. That'll be -40 because it's an odd power. -2 squared is 4 times 3 is 12 minus 6. -34. Okay. But thankfully, because of f being a polynomial function, then we can use the direct substitution for that, and we would get the same answer. But this, I just used this example to break down our techniques for sums, differences, and constants, so that you can just have an example of that. Okay, if q is a rational function and a is in the domain of q, then we can do a similar thing using the quotient. This example's on the next page, so we're going to work this example next. Okay, so this is our next one. Just to get some practice on the quotient technique, we're not going to break the entire thing down in the numerator like we just did, because I've established that with one example. But let's look at, I can break this as limit of the numerator, the polynomial in the numerator, as x approaches 3, and divide that by the limit of the function in the denominator as x approaches 3. And so I just want you to see this as well, how it works with division. Now granted, we know that we can go in here and break all this apart like we did previously. It just gets to be a lot of work. So we get to appreciate our theorems and our corollaries for what they allow us to do. Okay, so now we're going to just do a direct substitution from there. So in the numerator, tell me what we would have. We would have 5 times what? 3 squared minus 2 times 3 plus 1. And then in the denominator, 4 times 3 cubed minus 7. So 3 squared is 9 times 5 is 45. Go ahead and just simplify this, do the calculations. And I finished with 40 over 101. Okay, using our limiting techniques, we can rewrite this. The limit of the numerator divided by the limit of the denominator. Okay, using our techniques, we can also do the sum of the limit. The limit of the sum is the sum of the limits, so we can break this term and this term. And then in the denominator, you can break this term and this term. Okay, so we rewrote that. Also, I pulled the constant 3 out front. I didn't make a separate step for that. And we're not going to break this one down again just yet. We can go ahead and substitute from here. I think it's redundant enough at this point with the technique. So let's go ahead and substitute and then check your answer. Okay, substitute those in here. Gives us 4. This is the square root of 4 times 2, so the square root of 4 is 2. 2 times 3 is 6. Square root of 2, that simplifies there. This simplifies to just 2. a common divided 2 out of everything, and we're left with 2 plus 3 square root of 2.